My name is Svetlana Isakova, and I'm a developer advocate at JetBrains. This talk discusses only the specific story, specific functionality, Kotlin coroutines. Request standing behind Kotlin coroutines is to simplify the way how we do asynchronous programming. And we can say it is a new way to do asynchronous programming. However, in fact, it is old and forgotten way to do asynchronous programming. Coroutines were used to model to do asynchronous programming even before several threads appeared, before the concept of threads and several processors appeared. So it was used to model asynchronous computation back in the 60s in academia, and now we restore this concept to use for pragmatical use in industrial language. It is inspired by many other languages and many other approaches. Async-await in C#, coroutines and channels in Go, coroutines and channels, and many more, as I've already told you. However, the same exact solution is not present in any other language. So the whole story is now unique for Kotlin, despite it shares some ideas and approaches with other languages. At first, I want to discuss motivation. Motivation is simple, just avoid callbacks. I will repeat it one more time. Then we are going to focus our attention on suspend functions, functions that magically can be suspended. Then we will discuss the concept of coroutine, then structural concurrency, and at the end we will talk about channels. At first, what is our motivation? Let's say we have time-consuming operation and we try to do it from the main thread. You know it is forbidden. It won't work because it can block the user, and modern applications, modern system even don't allow you to write such code and to run such code. You'll get exceptions. How we can solve this? One of the ways is to use callbacks. To solve this problem of blocking the user, you extract the second part of the computation in a callback, in the Kotlin case inside lambda, and provide this callback as an argument on some, in our case, one complete function. So the idea here is we divide our computation into start and callback. And that works, that already used in many use cases, in many languages. However, we can do better, and we can solve the same problem of not blocking the user by writing the code very similar to the wrong one. However, somehow it works correct and doesn't block the user. I haven't yet explained what is await, how it works. It's just a very minor example for illustration what is our goal. Our goal is to write straightforward, simple code that somehow works without callbacks. Async-await is a feature already available in C#, so it's something known and used for many years, successfully in use. Kotlin uses the same idea. You can use the same functionality of async await, but in Kotlin, async await are functions. In C#, async await are language feature, while in Kotlin, it's just functions. So in Kotlin, async await are functions defined in the standard library that use the language support for coroutines. Let's look at another example, how coroutines can help us to simplify the regular code that we often have to write. And afterwards, I will more fully introduce this concept of coroutines. So far, we have this idea that, okay, we want to avoid callbacks, and we somehow achieve that by using language support of coroutine. Example. Let's say we have simple logic. We do actions one after another. At first, we use some network request, some authentication service to load ID for our user, given his or her email. Let's say here we use some service. Then let's imagine we have to send a request to a remote database, again via network request, to load some data about our user. Finally, we'll show the results. And here, these two operations, because they require some remote services or network connection, they can block our user. So they are possibly time-consuming operations, and we need to think carefully when we write code that works with such operations. We can just write this code line by line. First, authentication, then remote request, then showing the results. However, this approach is simple, but not recommended, because it can block the user or block the thread you run this code on. So it's not entirely wrong, but now we try to avoid writing code like this, not to block the underlying thread or not to block the user if we run it from the main thread. What solutions do we have? We can extract these actions into callbacks, right? And if we use Java 8 and completable future, you would probably write the code like this. First, doing this service, now we change the types of our function, the result types. Now it returns us some future type so that we can provide actions to be performed after we have the result, after we get the result. And we call this function providing action, what should be done after the result is available, then providing another action, what should be done after the second result is available. And for our simple use case, it looks a bit overcomplicated. The same can be done with RxJava. You use RxJava often, so this code should be familiar for you and clear for you. Now we again change the types of our functions. Now they return as probably the single value. And here we use the full power of reactive streams, basically just to do one operation, to do these operations one after another, step by step. It's possible solution. It works for many use cases. However, our approach, our idea, when coroutines might be really helpful is that such code for many simple use cases look overcomplicated. So reactive streams work well when there are actually streams and reactive streams, but for simple scenarios, when you just access a couple of services, it might be overcomplication over the code that we have written at the first slide. At the first slide, we have just written login, load, show. Here, it now looks really like it uses, especially my favorite is flat map here. Like you really have to think in terms of flat map in order to grasp the meaning of this functionality that it indeed we should call flat map and other stuff here. So it really brings a lot of complexity to solve often very simple issue, to solve a very simple problem. We can use the approach similar to async await in C#. Here, instead, now the code looks not that complicated as with callbacks. For simple scenario, it looks straightforward, line after line. Here, we still return the future, and like now in Kotlin case, it's called deferred, but it's essentially the same idea, the same as completable future or single. And then you can call await to await the result of the asynchronous computation. So here we somehow suspend our computation and continue when we are done. This approach is much better than before, and it already used in C#, and C# has both approaches. They have both async await for simple scenarios and reactive streams for complicated ones. However, in Kotlin case, we can do even better than that. We don't need to return futures and call await on futures. We can rewrite this code using suspend functions directly. And now our function returns what it returned before. In my very first slide, which was wrong, login function just returns user ID, load function just returns user data, and that's it. The only difference we made is this suspend modifier. So we added suspend modifier. Now we defined all the functions as suspend functions, but the result looks exactly like the initial code, the initial wrong solution that blocked the thread. But now the solution with coroutines for simple use cases like this one looks really straightforward and easy to read and understand. However, it doesn't block the thread. It doesn't have this problem underneath. So Kotlin coroutines bring this new concept of suspend function. Function that can be suspended. And we somehow change, so we, instead of blocking the thread, we would suspend our computations. Now I will illustrate how exactly it works, what happens, what the machinery, how this machinery works. But the idea is that now, with the help of suspend functions, we can write the code in a similar way that we used to write when we could naively block threads. So that is the basic idea. So you can define a suspend function in Kotlin. Then there is a question, where you can call such a suspend function. Suspend function is something that somehow can be suspended. We'll discuss details very soon. But so far, is it possible to call a suspend function everywhere? No. Suspend function is a special function that can be called only from coroutine or another suspend function. And now appears this concept of a coroutine. So coroutine is something, is a computation that can be suspended, is a place where you can call suspend functions. Now let's discuss what a coroutine is, what it is. So here we make the transition from threads to coroutines. Before that, we worked with threads, but now instead we start working with coroutines. Coroutines run on top of threads, but you work instead with them directly. And now we replace action of blocking thread, which was expensive and undesired, with the action of suspending a coroutine. Blocking thread is expensive, and sometimes you can't do it, while suspending coroutine is cheap and it's always possible. So coroutine, in essence, is a computation that can be suspended. So now what is suspended? What does suspended mean? So you can think of a coroutine as a small computation then you can run on top of thread. Here I will use the following notation. Thread will be line and computation will be some rectangle. So here I can start coroutine on a thread, and then I can at some point say that this computation gets suspended. So what it's done, how it works is Kotlin compiler takes this computation from the thread, it stops it, pauses it, and stores this computation somewhere in memory. Meanwhile, thread is free to be occupied with other tasks as activities. It is not blocked. Now you can run other computations on thread. And when the result is available, the computation can be restored to a thread. So when we were talking about sending network requests, for instance, we can start coroutine that sends network requests. It sends the requests. When it awaits for the result, it is stored somewhere in memory, it is suspended, and then when the network requests returns the result, this coroutine is restored to the thread it runs on. So that's how we changed blocking thread to the mechanism of suspending the coroutine. Thread is now free for other activities. It's not blocked. The question, how to create a new coroutine? You just use one of so-called coroutine builders. It's a library function that starts a new computation. For instance, you can use async function that starts a new computation asynchronously. This async does the same as async keyword in C#, but then it was special keyword that started new computation asynchronously. In Kotlin case, it's just a function. Or as an entry point to coroutine part of application. So now your application will be divided into suspend functions and regular functions. And to go from regular to suspend functions, you would need to start new first coroutine, and it can be started in a blocking way to await for this result using run blocking. Now let's return to my first introductory example with the image and see step by step how this mechanism of suspension works for this case. So here we have two functions, process image, the first computation, that inside loads image and calls await on it, and then when the image is loaded, it shows the result. So I want to demonstrate the mechanics, what happens when we write this code. So first, async creates a new coroutine and starts a new asynchronous computation. Here, load image async started new computation on the thread. Then, await is one of so-called suspension points. That is trigger that can suspend coroutine. When you call await, that means that our coroutine can be suspended. So here, when we call this await function, await is just defined as a suspend function in the standard library. So basically, every suspend function is a suspension point. Every suspend function might be trigger that suspends coroutine. When we call this await function, there is a line-by-line example. We start with process image, it starts computation. Then load image async starts new computation asynchronously. And the reference to this load image async is stored in the deferred variable. So deferred stores the reference to this computation. Then, when the code reaches await, it is trigger that suspends their outer computation. So here, await what triggers the compiler to suspend this process image computation, and it gets suspended. It now stored somewhere in memory, and the thread is free. The thread can be occupied with other activities. If it's main UI thread or any other thread, it's free. Then, when the load image async returns the result, the image is loaded, it triggers back the suspended computation and returns it to the thread. So when image is loaded, our suspended computation is returned. Under the hood, this magic works via the same callbacks as we were discussing at first, but these callbacks are hidden inside this suspend machinery. You don't work with them directly, you just write this simple, straightforward code. So here we returned coroutine. If we look back at our show user example, this one has many suspension points. So here we have two. Login is network request, so is a suspension point. When we run show user from some coroutine, it first runs, it reaches the login stage, then when it expects results from request, this coroutine gets suspended, and when it receives results, it gets restored, then it reaches the second network request, it gets suspended, and so on. Then it gets restored and continues its execution. That's why you can write this code very straightforwardly, just line by line, action by action, without difficult API or confusing API of some special libraries. You just write it line by line, and you see that the underlying thread is free when you do some network request. So that demonstrates how this example works, why it doesn't block the underlying thread, why it's possible to write this simple code line by line, because the thread now is free while waiting for network result. Suspension points are just calls of suspend functions. So whenever you call suspend functions, IntelliJ highlights that there is these suspension points the moment when your coroutine might be suspended. You can ask which coroutine gets suspended when a suspend function is called. The answer is straightforward. The coroutine that contains this suspend function, the coroutine you call this suspend function from. We saw this constraint that suspend function can be called only inside other suspend functions or inside coroutines. That means that each suspend function is called from some coroutine. And here, when you create a sink, when you start a new coroutine, these curly braces, it's lambda curly braces, they correspond to coroutine that can be suspended. And when we run this coroutine, show user when it reaches suspension point, then this coroutine created by a sink gets suspended and then restored. If you inquire what exactly triggers the suspension of coroutines, so these some implementation details, then we return back to how to use this. There is a special function called suspend coroutine that actually a language mechanism to suspend a given coroutine. And when you call a suspend function, you finally will somehow call this suspend coroutine by using await or other library call. All these library functions will refer to suspend coroutine. But you never probably use it directly. It's like language support for this suspension mechanism. And the triggers that call this suspension might be different functions in different libraries, including await and other libraries. For instance, right now, Retrofit supports coroutines, and they provide the way to perform network request as a suspend function. So they just give you this support via their library. And you just define different suspend functions in your application that under the hood will use library support. And that turns out to be really convenient and flexible. Your code really looks very straightforward, very simple, but under the hood, you just use these suspend functions. When you suspend coroutine, it stores all the call stack. So it sees the call stack, which calls this suspend coroutine. It stores it in memory together with the state of local variables. And coroutines are relatively cheap because only one object is used to store the whole coroutine. They are much cheaper than threads. Thread requires several megabytes, I think, 2 probably, or more, and coroutines several kilobytes, hundreds of kilobytes or so on. So it's much cheaper. You can create much more coroutines, and in general, it's cheap to create coroutines, suspend it, create lots of coroutines for different tasks, and so on. So you don't need to reuse them. You just create and destroy. They are very cheap. And when you resume coroutine, you restore this call stack. So you restore it from memory and continue its execution. So it's how the compiler supports this coroutine machinery. As I've told you, under the hood, these suspend functions are implemented via the same basic callback mechanism. Each suspend function has a secret continuation parameter in the bytecode level that is a generic callback interface. So under the hood, this suspend magic works via the same callbacks, but now these callbacks are hidden by the compiler and you don't work with callbacks directly. Kotlin compiler makes everything, all the changes automatically. You can ask, on which thread does the coroutine resume? And the answer is that you specify that by yourself. You specify the context on which a given coroutine can be run. It might be context thread from the thread pool, or you may want to run this coroutine on the main UI thread only. The correct way to say here is not run, but schedule, because when you want to start new coroutine on the main thread can be busy at the moment. So the coroutine automatically waits when the thread gets free, and after that it runs. So it's more correct to say schedule here. And also, when we're talking about running coroutines on thread pools, they are not attached to threads, and coroutine can be continued on any free thread. So it just uses all the threads from the common thread pool. Coroutines can be nested. You can create one coroutine inside another. You can start new coroutines from different coroutines. And there is a question. Is there any relationship between parent and child coroutines? So when you nest coroutine, you have parent coroutine and child coroutine. Are they somehow connected or not? And the answer is yes. And that brings us to the next topic, to the next important story about coroutines, which is called structured concurrency. And that is something also novel in Kotlin, because before that you have to manage the dependencies by hand, dependencies between parent and child coroutines. But with structured concurrency, it happens automatically. And historically, the coroutines were released in an experimental state for 1.1 and 1.2. And 1.3 release brought coroutines to stable. And with this change, it also brought the concept of structured concurrency to the picture. So it was something that based on feedback gathered from usages from the community. So what is the example? We have, let's say we now do several asynchronous computations in parallel, like we have enough threads, and we want to do our computations in parallel. We have simple example. The function that mixes two images somehow, and another function that loads two images in parallel and then applies overlay to these images. So we start two computations, two coroutines, two asynchronous computations. This one just returns reference, and it is started in parallel, so the main coroutine continues and launches second coroutine. This line returns the reference, and only after the first await is reached, the main load and overlay coroutine gets suspended, waits for the result, and then when the result is available, it gets back on the main thread, on its thread. The question here, like it all works fine and well. The question here, what happens if one of the loading throws exception? So what happens if exception is thrown inside the first child coroutine? We have a problem that the second image continues to be loaded, right? You have to explicitly cancel it somehow. You have to explicitly catch this exception and check the state of the second image and cancel it. Structured concurrency tries to fix this problem. So again, let's say it fails, then the upper coroutine fails, and unless it explicitly cancels the second coroutine, the red one leaks because it just continues its execution. It continues to load image. But we are no longer interested in it because we already have exception. With structured concurrency, we can solve this problem by introducing scope, and scope will be responsible for cancellation of children coroutines if some error occurs. So now, after introducing scope, if the first coroutine fails, this scope catches the exception and automatically cancels all other coroutines started inside the scope. So you no longer need to write this code by hand. It automatically written in the library and it automatically works for you. So it really, to a great extent, simplifies the code that you're writing when you have several coroutines, when you start coroutines from another coroutines. So it catches exception, now cancels the second one and fails. So this problem is solved just by introducing scope. So coroutine scope waits for completion of all the child coroutines inside this scope, and this is another quality, helpful quality of the scope. It will automatically wait for completion, and what we already discussed, it cancels all the children coroutine if there is an error. And before Kotlin 1.3, you could start coroutines everywhere from any point, and there was no relationship between different coroutines. Right now, in current version of the library, you can start a new coroutine only inside the scope, either explicitly inside the scope or inside global scope, but this is not recommended. Only as a major coroutine, top-level coroutine, but in general, use scopes. Each coroutine has the corresponding scope. So when you start global coroutine from global scope, it automatically has the scope in which you can start different coroutines, and that's how the relation between parent and child coroutine works. It just works using scopes. So scope is mechanism to provide the relationship between parent coroutine and child coroutine. You can regulate this relationship, and using scopes, you get all the benefits out of automatic cancellation for free. So now the lifetime of coroutine is bound to lifetime of the parent scope. And the general idea here is to bind all the coroutines to some element inside your application, to some element with a lifetime. So, for instance, in Android, the first idea was to bind coroutines to activities, to create a scope for an activity and start all coroutines from the scope. Now, the recommendation is to bind it to data view elements. So there are you can read the details in the documentation and in the online. In there some recommendations from Google, but idea is that you find the natural object with life cycle in your application and bind coroutines to this object. And if you have server-side, you have also some elements with a specified life cycle. You can bind coroutines to this object or just to the whole application via global scope. It's also possible, but then they will be cancelled only when the application stops. Overall, structured concurrency brings structure to the picture and saves you from writing lots of manual code, manual error handling. It all is done automatically under the hood in the library. So it's hidden from view, but it works from you for free. So now I still have some time, and I want to cover one more topic about coroutines. And this is about sharing information between different coroutines. So when you started a couple of coroutines, how to share some data between them? That's the question. And the answer follows the Go programming language, where the concept of coroutine is available for a long time, and they use channels for that. So now I want to briefly highlight what a channel is and how it can be used for sharing something between coroutines. And following Go, we prefer to highlight that it's not synchronization between coroutines, but rather communication between them. So different coroutines can communicate, can send messages to different coroutines via channels. So now, instead of sharing mutable state, we share by communicating. So it's the same approach, it's a bit different approach, but it follows some best practices of other languages like Go. And now, instead of synchronization primitives, we have communication primitives, and channel is such a communication primitive. So channel is a very simple thing. You can send information to it, one coroutine can send information to it, and another coroutine can receive information from it. It solves typical classical producer-consumer problem. Several coroutines can send some information to it, and several consumers can receive information for it. So we call these coroutines producers that produce some data or some information, and those ones we call consumers, and there might be several coroutines on each side. Send and receive function are defined as suspend functions, so it uses this mechanism of suspension. And also there are two different interfaces, send channel and receive channel, and you share the same channel with producers as send channel, and you share this channel with consumers as receive channel. So you clearly say that which coroutines can only send to it and which coroutines can only receive from it via interfaces. There are different types of channels. Unlimited, the one that can store lots of items, lots of elements. The one that is buffered, that is limited, that can store only fixed number of elements. The one with buffer of size null, of size 0, that is called rendezvous channel. And I'm going to highlight this one right now, how it works. And the last one called conflated, which just loses the previous elements, that just returns the last element that was shown. When someone calls receive, it just receives the last element that was added to this channel. So I want to make a stop at rendezvous channel semantics. And its name, rendezvous, means a fixed time and place, when a fixed meeting time and place. And here, an element is transferred from sender to receiver only when send and receive methods meet in time. So there is rendezvous. And send suspends until someone calls receive. Receive suspends until someone calls send. Illustration. Here, for simplicity, we'll have one producer and two consumers. Producer will send two tasks to the channel. So we create a channel, and we send a couple of tasks to this channel, and then we close this channel. So just simple task. Consumers will have two consumers. Here we start two asynchronous computations if you have several threads in parallel. And each consumer receives one element, receives its task, and start to process this task. Very simple. How it works. So we created a channel. You see we have now 3 coroutines that can run on different threads in parallel. So let's imagine that first starts consumer coroutine. Consumer coroutine calls receive on the channel, but there are no elements in this channel. So, and receive is defined as suspend function. So now this coroutine suspends, waiting until someone adds element to the channel, waiting for send invocation. Now it suspends. Then, say producer coroutine starts and sends the first task to the channel. Now the rendezvous happens. Send and receive calls meet in time, and an element can be passed to the consumer coroutine. So consumer coroutine is resumed. They can be run in parallel, so we don't know what happens first, but let's say it resumed. And it receives the element that was sent, and it starts to process the task, the first task. In the meantime, the second producer coroutine, so the producer coroutine, sends the second task to the channel, but there is no receive call. And because of that, this coroutine suspends, waiting for receive. And when the consumer coroutine starts and calls the receive call to receive an element, the rendezvous happens, and the element is transferred from producer to consumer. Now the second coroutine also processes the task, and this producer can close the channel. So yeah, now our two consumers process our tasks. The same can be done with many tasks. Here we send several tasks from the producer to the same channel. And now we will slightly change the code of consumers. Instead of calling one receive, we can iterate over channel, and under the hood, this for loop calls receive while iterating, and writing this code will allow us to receive elements one by one when they appear, and suspend if there is no elements. So each element will go to one of the coroutines when it calls the corresponding receive method. So that's how channel works. It's a useful way to share information between different coroutines. It's also not something new. It's already in use by the Go developers. They have the similar concept of coroutine and channel, and they successfully use channel as these primitives of communication. And now we have the same in Kotlin. The same idea, just Kotlin implementation. The last thing I won't go deep here into details. It's something available so far in an experimental state, but it is something that is going to be added to the library. So basically, when we introduced coroutines, there was a question, what should people use, reactive streams or coroutines? There were many teams that were already using reactive streams, and they were interested whether they need to convert and what benefits do they have. And the answer was that if your application has natural stream of events, like the hot stream of events or cold stream of events, when it's naturally appearing somewhere, when you can just observe this stream of events and it naturally fits your application, then probably you are already satisfied with reactive streams. However, as I've shown you in the first example, there are many cases when reactive streams bring some overcomplication to simple code. So the code that you can write in a simple way, line by line, like my show user example, with reactive streams, looks really complicated. I mean, this one, we can rewrite with reactive streams. It looks a bit unclear, confusing, in comparison to the code that we can write with coroutines. So that was the answer, that if you have code like business logic, a lot of code like business logic, probably you can win from using coroutines because they will simplify your code. However, if you have reactive streams, then they already work great for you. Now, we understand, and there are many cases when reactive streams fit perfectly to the task, when there is natural flow of events or stream of events, and then reactive streams are really useful. And because of that, now the authors of coroutines library want to bring reactive stream, suspend-based reactive streams to the coroutine library. So now, if people use coroutines and they need reactive streams, they can use Flow. So that is something so far in experimental stage, but it is going to be released really soon. So here you have API more close to Kotlin standard library than to reactive stream, but the idea is the same. You have flow of events and you can manipulate with it and observe the result. Note that it doesn't implement the same API as reactive stream because it is suspend based. So all these functions are suspend functions. That is important difference, and it is important benefit because in RxJava there was a complication with back pressure. It's not easy to implement custom operators because you have to think about back pressure. In Kotlin Flow case, back pressure happens automatically, pushing information back to the source of events happens automatically thanks to suspension. So that is the major benefits of Flow in comparison to RxJava, because they have this suspension machinery under the hood. There is a way for integration with RxJava, so you just use extension functions Flow to publisher or publisher to Flow in order to convert one to another and back. So there is a way to provide this integration when you want both benefits of coroutines and benefits of reactive streams. So that is something that will be available rather soon, but even now you can use preview, it's almost final preview, to work with it. So that I'm finally done. That was my presentation, all the topics I wanted to cover today. More about coroutines. There was a question about whether there are some real life stories, people who already use coroutines. I just want to highlight a couple of talks from Kotlin Conf that will be this year in December. There were several submissions, but I think only these two made into. This is exactly case studies, like how people use some examples of usages, coroutines in their applications, but we already know that many people are using coroutines, and now it's even kind of default Google recommendation. So the best practices, some of the best practices are still developed, but the general idea that we are moving to coroutines, and coroutines might be really beneficial for server-side development as well, because of this not blocking thread, but writing simple code idea. So coroutine support is the language support. Everything else lives in a library. You can work with it, play with it. We have you can find there a lot of documentation about coroutines. There is coroutines guide that introduces the concept. Recently, we've also published the so-called hands-on lab. If you want to play a bit with coroutines, you can use this, read it and do it step by step. It creates, it showcases some usage of coroutines and compares it with other approaches. And if you want to watch more talks about coroutines, I would highly recommend Roman Yelizarov talks. There are many from different Kotlin Conf conferences, and he is the main creator of the library and of this idea, so he's just the main source of the concepts. And here, Kotlin coroutines in practice, he actually introduces the idea of structural concurrency, because before there was no structural concurrency, but here you can historically see how it was introduced, like that before it was there was no such concept.
I have a question on channel. So I saw the channel has a sender side and receiver side. Mm-hmm. Yeah, so sender push the values on the channel. But so what I wanted to know is, so who manage the value? I think the channel is some kind of queue. Right?
Yes, who produces? The producer produces the values. Mm-hmm. It's just means of communication. Mm-hmm. So producer generates values. In my case, I omitted all the details because they are not important for us. I just create task, but the producer here generates some data.
Yeah. So mm-hmm. who manages the queue? The data?
Who manages is channel implementation.
Yes. Actually, which side? The producer side or receiver side? Which side manages the channel?
You see that in our code, we created a channel, and then we pass reference to the channel to coroutines. So here we just created the channel from some code, right? So we, at first, when we use channel, we need to create it. Then this reference is passed to producers, to different coroutines, producers and consumers. And they just access this channel via this reference. And it's an object stored in memory, created and stored. And for instance, this code can finish, so we can return from this code, but our coroutines will have the references to the channel, and when they call methods, this queue is this functionality, this send calls this functionality to manage the queue.
What's the main goal to support rendezvous channel? I guess that it guaranteed the message delivery sequence. Am I right?
I would say that in real life, you probably just use buffer channel.
Yeah.
Yeah, so the rendezvous channel, like I use it as an illustration of this rendezvous idea, but the same rendezvous approach happens here when the buffer is full. So you can use, like, you can store 4 elements in a buffer, or, I don't know, 100 elements in a real-life scenario, and when the buffer is full, the next send that sends, in my case, 5th element, gets suspended. So the same rendezvous approach works here as well. It's just this one is better suitable for presentation purposes, for explanation, but the same idea applies here.
As I understood, the buffer and the rendezvous is guaranteed together some message delivery sequence, but the rendezvous module guarantee more advantage. That is just overflow, buffer overflow.
No, but there, in this case, buffered and rendezvous are very similar, and rendezvous channel is actually buffered with the buffer null 0. And it's just the same, but without a buffer. And this one is rendezvous channel with additional buffer to store elements. So here, when we send, it can be stored somewhere and returned when someone receives it. You can also use unbuffered channel. Unbuffered just has this possibility of memory overflow, because if you send too many elements, they're just stored, but for your purposes, it can be enough. And in this case, send never suspends, send always sends, and receive suspends if channel is empty. So thank you a lot for your attention, and have a nice Kotlin with coroutines. Thank you.